We've seen this special set of numbers that lie on the unit circle have the property that when we raise them to a power or multiply them together, we just rotate round and round the unit circle. Let's explore that a bit further because it allows us to define the exponential function, and it obeys some incredible properties as we're about to see. So let's begin with a number on the unit circle, again where theta is a real number, and let's consider this number cos theta plus I sine theta as a function of theta. So let's write this as f of theta. Now we've seen that it obeys the following properties. If I take the product of two of these, it's the same as the function adding the arguments together. So f of theta times f of phi is f of theta plus phi. We've also seen that if we raise it to some power, that becomes f of n times theta. And if we divide two of them, so it satisfies a bunch of properties that we've actually seen before. But before we see exactly what it is, let's consider also the derivative of this function. If I differentiate the cos, I get minus sine theta, and the derivative of the sine becomes cos theta. So this is equal to I times cos theta plus I sine theta, which if I write it in terms of f is I times f of theta. So again, another peculiar property of this special number. If we just think back to real numbers, we've actually seen all of these properties before in the exponential function. In fact, for real numbers, if I take the derivative of e to the ax, then that's equal to a times e to the ax. And the exponential also obeys the properties that if I multiply two exponentials together, I add the powers in their arguments. Now, if I just replace a by I in this formula, I've got exactly the equation. And so this leads me then to conclude that cos theta plus I sine theta is actually e to the power I theta. It's quite an amazing result. It's known as Euler's formula. And a few amazing identities follow from it. If we think back to De Moivre's theorem is just a statement that e to the I theta to the n is just that if I raise e to the I theta to the power n, that's e to the I n theta. We also have things like the conjugate of e to the I theta is cos theta minus I sine theta, which is cos of minus theta plus I sine of minus theta, where I've used the fact that cos is an even function and sine is odd. And so therefore this is equal to e to the minus I theta. So conjugation is the same as a reflection in the real axis. Also note another key identity, that if I add on an integer multiple of 2 pi, then because cos and sine are periodic with period 2 pi, that's equal to just e to the I theta. Let's have a look at a few numbers on the unit circle and write them in the form e to the I theta. Let's start here with the number 1. That makes an angle 0 with the real axis, so that's easy. It's just e to the I to the 0. What about the number I? The argument of I is pi by 2, so I can therefore write that I is equal to e to the I pi by 2. Very neat formula. Let's continue round the unit circle to minus 1, and that's got an argument of pi, and so I can write that minus 1 is e to the I pi. Similarly, minus I is e to the minus I pi by 2, because minus pi by 2 is the principal value of minus I. And remember that we can add on any multiple of 2 pi I to the complex argument. So in fact, number 1 is also equal to e to the I times 2 pi. Similarly, other numbers on the unit circle, if I take the number 1 over root 2 times 1 plus I, then that's e to the I pi by 4. So some very special numbers emerge once we have the complex form of the exponential. And in fact, now that we have this form for cos theta plus I sine theta, we can use our modulus argument form for complex numbers to write down complex numbers using the complex exponential in what's called the polar form of complex numbers. For a general complex number, which has a modulus and a principal argument, which I'll write as arg with a capital A to denote the principal argument, is modulus of z times e to the I times arg z, or just r e to the I theta, where r is the modulus and theta is a principal argument. And so in this form, multiplication becomes easy. If I have two complex numbers z1 and z2 in polar form, then multiplying them, so I multiply their moduli r1 and r2, and I add the arguments theta1 plus theta2. So the polar form is an incredibly useful way to write down complex numbers, and we'll use it more often than not. So we've defined the exponential for a purely imaginary number, and in fact it's not too much of a stretch now to define it for any number, any complex number. The complex exponential, if we have z is x plus iy, then e to the z, and given that x and y are real, I already have this then as e to the x, which is always positive, it's in fact the modulus of e to the z, times cos y plus I sine y. So the argument of e to the z then is y plus 2n pi. All the usual properties of the exponential function apply. Given the exponential, can we define the logarithm? Well, we can, but we have to be a little bit careful. Suppose we have e to the z equals e to the w. Within the set of real numbers, we would just equate z and w and be done with it. But with complex numbers, we have to be a little bit careful. So let's let z and w be written in Cartesian form with real numbers a, b, c, and d like this. Then what we have, equating the modulus and argument of e to the z and e to the w, e to the a is equal to e to the c, and so because a and c are real, a must equal c. So that's nice and easy. Now, with the arguments, we can only equate them up to factors of 2 pi. So b must equal d plus 2n pi, because I can add on any multiple of 2 pi that I like to the arguments. And so therefore, the solution to this equation is going to be, where w equals c plus id, we have a plus a multiple of 2n pi. And so w then is equal to z plus 2n pi I. So taking logarithms, we need to be careful of this fact. And in fact, the complex logarithm is defined using this. So the logarithm function is defined as log z, the log of the modulus of z, plus I times the set of arguments of z. So that is, it's a multi-valued function. It doesn't have just one particular solution. We can now evaluate things like the logarithm of -1, which is just log of 1 plus I times the argument of -1 is minus pi or plus pi, and we can add on integer multiples of 2n pi to that for n in z. So it's a purely a set of imaginary numbers in this case. Similarly, the log of I is also the log of 1, which is 0, plus I times, it's again a set of points on the imaginary axis.